Swayam Prabha. Digital India. Educated India.
Good morning. Today I'll discuss about the equation of motion in rotating frame of reference. Contents of the lectures are turbomachinery flows. I'll discuss equation of motion in rotating frame of reference. I'll illustrate the effect of Coriolis force on a radial flow impeller, an axial flow impeller, and mixed flow impeller. Then I'll move to energy equations in rotating frame of reference, illustrates on a radial machines and then axial flow impeller. With respect to turbomachinery flow, I like to state that the advancement of turbomachinery has been feasible because of appreciation of flow and heat transfer within the blade passage. And flows in turbomachinery changes continuously the frame of reference. To illustrate this, I like to discuss the flows within a turbomachinery. As an example, here I have taken a centrifugal machines. Now in the centrifugal machines, air is sucked by the impeller and the fluid is churned within the impeller and then forced to the volute casing where the kinetic energy changes to its pressure. Now if you concentrate on the flow within the impeller is completely unstable. If you look from outside, at every instant, the flow field within the impeller changes. So thus, with respect to an absolute frame of reference, it is very difficult to analyze and give some analytical expression for the fluid property as it changes or as it passes to the impeller. So therefore, we describe the flow field within the impeller in relative frame of reference. So here, when I describe the flow field within the impeller, I'll prefer to describe with respect to relative frame of reference. Similarly, suppose flow within the volute casing, I'll describe with respect to absolute frame of reference. Now, what is relative frame? What is absolute frame? I have written here. Flow field through the stationary component of a turbomachinery, such as stator blade, and the casing is referred to the absolute frame of reference, whereas the flow field within the rotor, which is attached to a spinning shaft, is discussed with respect to the relative frame of reference. Therefore, the flow within the blade passage or a rotor passage, I'll refer with respect to W, the relative velocity. Whether in a stator, I'll discuss with respect to absolute velocity. Hopefully, I have made you understand what is important for a turbomachinery to discuss the flow field in relative frame and absolute frame of reference. And you hope you have appreciated my statement here that the flows within the turbomachinery changes continuously the frame of reference as it moves from the rotor to the stator. Regarding discussion of relative and absolute velocity field, you can analytically evaluate the relation between the relative and absolute velocity as from the absolute velocity, if you subtract the tangential component vectorically, you would get the relative flow field. Now, there is another statement is the relative flow within the impeller is steady. How? I have already told, if you stand outside and if there is a transparent impeller is being made, then you will realize that flow field at every moment within the impeller is changing. So absolute flow field, as I have told earlier, is completely unsteady. Then how the relative velocity would be steady and how the proof can be given to you? If a camera is tied with the impeller and if it takes photograph as it moves along with the impeller, and then it would capture the relative flow, and then the streamlines will appear steadily and it's moving smoothly within the impeller passage. With this example, I am confident that one can appreciate the relative velocity within the impeller passage is steady. Furthermore, the quantities like velocities, acceleration, rotation, tensor undergoes changes while moving from stationary to rotating frame. I think you can appreciate, because velocity, relative velocity and absolute velocity is vectorically related with the tangential component. So the quantities of absolute and relative velocity, they are different, and thus the acceleration and rotation tensor in both the frame are different. Now, further to discussions, let's discuss on rotating or moving frame of reference. Now, Newton's law, that is P is equal to mf, is the basis of all machines, which is valid while the frame of reference is at rest or translating with uniform velocity. And the frame of reference where the Newton's law, that is Newton's second law of motions, can be applied is called Newtonian frame or Galilean frame of reference. Thus in turbomachinery, where it is spinning with respect to an axis, particularly for the impeller, the equation of motion needs to be modified because your frame of reference is neither at rest nor at translating with a uniform speed. So the important point is, for turbomachinery, which is rotating with the axis, the equation of motion needs to be modified. Now the equation of motion can be derived in a frame of reference which is rotating with the angular velocity omega. Then it can be expressed as mf is equal to p minus m twice omega cross w minus m omega cross rho. Thus, there are two additional inertia components. Now, m is the particle mass, rho is the position vector of that mass. Now, this component m into twice omega cross w is called the Coriolis force, which is very important for turbomachineries. And this one, that is omega cross rho, is the centrifugal force, where w has a sense of velocity in rotating frame, that's the relative velocity. Similarly, f is the relative acceleration. Now, if you try to understand about the sense of the Coriolis force and the centrifugal force, their inertia component, so one can appreciate that omega cross w is a vector which acts perpendicularly to the plane described by the two vector omega and w. Similarly, centrifugal force, that is omega cross rho, is acting outward rather, and perpendicular to the axis of rotation. So everyone have some sense of centrifugal force, but hope you all are aware of about the Coriolis force, which is perpendicular to both the vector omega and w. That means it is perpendicular to the plane described by two vector omega and w. With respect to illustration, let us first consider the rotational effect on Earth. Now, I can tell you that whirlpool near the northern and southern hemisphere that occurs is because of Coriolis effect. I have considered the Earth rotations, and let's take a region in northern hemisphere, and that location I have marked by a small element which has been zoomed here. At the same time, I have considered the rotation of Earth and denoted as omega. Now, because of weather fluctuation, a local vacuum has been created in this region, and because of this vacuum, the air from surrounding region will rush to fill up the vacuum. And now, if we consider the Coriolis effect because of the rotation of Earth, the Coriolis component will be perpendicular to both omega and w, and thus I have illustrated the direction of omega cross w, which is the Coriolis effect. And because of this force, inertia force, what will be the resultant? Resultant will be the air will turn, resulting in a whirlpool. Thus, you have realized that whirlpool that occur near the southern or northern hemisphere is because of Coriolis component. Let us now focus on effect of rotation for turbomachinery. Now let's begin with a radial flow impeller, and here I have illustrated with a sketch of a radial flow machine. In radial flow machine, flow enters the machine radially and exits also radially. And I have considered the rotation, which is anticlockwise here. So rotational vector will be perpendicular to the plane of paper. To illustrate that, I have tried to draw a simplified sketches here, three-dimensional sketch, illustrating the omega vector, W relative velocity which is coming out of the impeller. So because of rotation, there will be a correlation component, and correlation component will act in tangential direction. If you vectorically see the direction of omega cross W, it will be perpendicular to both omega and W. So it will act in a tangential direction. Thus, one can appreciate in a radial flow machines, the energy transfer can be related to Coriolis force. There is no circulation and no hydrodynamic lift. On the contrary, for an axial flow machines, the energy transfer occur because of circulation developed along the blade and due to aerodynamic lift. To make you understand, I have taken a simplified sketch of an axial flow machines. So the impeller is connected to the hub, and I have considered for simplicity the meridional streamline lies on an axisymmetric plane. So radial shift of streamline has been neglected. Now if we project the blades on the plane of the paper, you will appreciate that flow is deflected as it passes through the impeller. So I have drawn the streamlines as the fluid passing through the impeller. And if we consider the aerofoil shape, there are concave and convex surface. On the convex surface, the flow will decelerate, the pressure will be higher. And on the convex surface, that is here, the pressure will be lower than the free streams because of acceleration of flow. And one can imagine that because of this pressure difference, there will be some effective lift. Now this pressure difference can be related with the circulations. Actually, the flow around the blade can be related with the circulation developed. If you take a imaginary circuit and if you calculate V dot ds, ds is the circuit length, you will evaluate circulation. We generally define aerofoil as such that aerofoil is a device that produces circulation. So I have tried to, in the next page, here I have given an example so that you can appreciate relation between the circulation and lift. With respect to that, I'll take you to the Magnus effect. I trust all of you have gone through about Magnus effect in your second year level of fluid mechanics. Now, rotating cylinder produces circulation around it, and if there is flow pass through the rotating cylinder, there will be a lift L, and the magnitude of the lift will be rho v into gamma, where gamma is the circulation and b is the approaching velocity, and the lift here is perpendicular to v. So similarly, if you compare with a rotating cylinder to the aerofoil, I have told you aerofoil is a device that produces circulation around it. So because of the circulation approaching velocity, there will be a lift which is perpendicular to c. C is the approaching velocity here. And here also the lift will be rho c into gamma. So I trust now you can appreciate how the lift is being generated because of circulation. So thus, in brief, in an axial flow machine, the work transfer occurs because of the circulation and aerodynamic lift. There will be no effect of correlation component for work transfer here. In a mixed flow impeller, here the work transfer occurs because of both correlation component and circulation developed around the blade. Now, I have already told you about the centrifugal force. M is equal to omega cross rho. And if you appreciate, or if you try to evaluate this omega cross rho, you will understand the magnitude of this will be r into omega square, where r will be from a point. If you draw the perpendicular to the spinning axis, the r is the perpendicular distance. So magnitude of this would be r into omega square, which is nothing but centrifugal force. Let us consider the flow field in a frame of reference which is spinning about an axis of rotation. And let's consider a streamline. And if you try to derive the energy equation along the streamline, we'll get the following conclusion. What is the conclusion? That for a compressible flow, we can define the relative total enthalpy, which is denoted as H0R. So H0R is nothing but H plus W squared by 2 plus G into Z minus R squared omega squared by 2. This R squared omega squared by 2 comes from the centrifugal force. Now, this first C, that is H plus V squared by 2 plus G into Z, you are aware with the corresponding total enthalpy. Here, we have defined now relative total enthalpy. So it's a total enthalpy in relative with respect to relative velocity. Another very important conclusion that we'll get here, for steady flow with no external energy added, the relative total enthalpy is constant along the streamlines, even if there is dissipations. So H0R remains constant along the streamlines, even with the dissipation. Similarly, we can, for incompressible flow, we can define relative total pressure, P0R, and P0R is expressed as P by rho plus W squared by 2 plus G into Z minus R squared omega squared by 2. Here you look the difference. For steady flow with no external energy added, the relative total pressure P0R decreases along the streamlines with dissipation. Here P0R decreases along the streamlines because of dissipation. However, your H0R would remain constant along the streamlines even with the dissipation. I trust you have understood the definition of H0R and P0R. I have summarized here what I have told in earlier page. So in brief, I like to say that for steady flow with no external energy added, total relative enthalpy remains constant along the streamline even with dissipation. However, for an incompressible flow, total relative pressure is constant when there will be no dissipation along the streamlines. Actually, if we go along the streamlines, between two points, the pressure difference will be the loss. Furthermore, I like to give you few examples on what I have told so far. Before that, I like to make a statement that for turbomachinery, there is no external work transfer in the relative frame of reference. Suppose if we be in a relative frame of reference, there will be neither work is added or energy is extracted from the fluid. Now, if I concentrate along streamlines in the flow field, and if I neglect the dissipation, I can express that P0R would remain constant. That means P0R is equal to P by rho plus W squared by 2 plus G into Z minus R squared omega squared by 2 would remain invariant along the streamlines. Let's consider 2 points, 1 and 2, along the streamlines. Then P0R1 must be equal to P0R2. So here please note that I have neglected the dissipation. Now, after this discussion, let me take you to an axial flow machine and a radial flow machine. And in an axial flow machine, you know the streamlines lies in an axisymmetric planes. And I have considered the meridional streamlines as I have shown. For the time being, radial shift of streamlines, as I have shown by red line, has been neglected. So what I can say, that if I consider the 2 points, say one at inlet and two at exit of the impeller along the streamlines, and if I neglect the radial shift of streamline, then there will be no effect of radius. That means here I can write P0 1R is equal to P0 R2, and there the effect of radius can be neglected. Thereby, change of static pressure between the inlet and the exit of the impeller will be either because of acceleration or deceleration of flow in an axial flow machine. Thereby, in axial flow machine, the pressure rise per stage is limited. But if you consider a radial flow machines, you see, as the streamline passes through the impeller, there will be a significant change of radius. So apart from acceleration and deceleration of fluid, the effect of radius will play a significant role. Thereby, change of pressure rise per stage in a radial flow machine is higher than that of axial flow machine. That we can easily appreciate from expression of relative total pressure. Now, let's come to the relative total enthalpy. Similarly, for an axial flow machine, and if the flow is compressible, I can write H0R1 between the 2 point, one at inlet and another at exit. H0R1 must be equal to H0R2. So H1 plus W1 square by 2 must be equal to H2 plus W2 square by 2. Thus, change of enthalpy will be only because of acceleration or deceleration of flow. But take a radial flow impeller, and here also H01R1 must be equal to H0R2. And if we write the expression here as I have written, then change of static enthalpy would be because of change of radius and acceleration or deceleration of flow within the impeller. Thereby, del H, change of enthalpy in a radial flow impeller will be much higher than that of axial flow impeller. Furthermore, I like to tell you that for an compressible flow, del H0 is the change of total enthalpy. Okay, not relative. Change of total enthalpy can be related to the Euler work for a machine, turbo machines. I'll define in the next chapter about the Euler work. And similarly for incompressible flow, please, there is a mistake, it will be incompressible flow. For incompressible flow, del P0 will be related to the Euler work. So for compressible flow, del H0 will be related to the Euler work, while for incompressible flow, del P0 will be related to the Euler work. We'll define Euler work in the next chapter. Thank you for listening.